Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be building off the last one where we talked about mid-latitude cyclones, and now we're going to be talking about tropical cyclones. Now, these storms typically form as tropical depressions, then move into what we call tropical storms, and then move into what we call, depending on your part of the world, hurricanes, cyclones, or typhoons. So let's go ahead and dive into what makes these storms tick. Really quick, just mentioning my reference materials again. Professor Ian M. Brooks, University of Leeds, Eric Snodgrass, UIUC, NWS, NOAA, and UCAR. I used that link in particular on the bottom from UCAR to help make this lecture. So looking at mid-latitude cyclones, just to recap, these are low pressure systems that are characterized by, or characteristic features of mid-latitude temperate zones. So think 30 to 60 degrees north and south latitude. They form in well-defined zones associated with polar fronts, which provide strong temperature gradients and convergent flow resulting from global circulation patterns. We've talked about all these before. So we're in particular on that GIF on the left looking at a storm that formed over southern Colorado. That was particularly impactful, as we mentioned at the very end of the last video. This is the process of bombogenesis, or the rapid intensification of a storm, at least 24 millibars decreased over 24 hours. But these are a little bit different than our tropical cyclones. So if we put them all together, for mid-latitude cyclones, we've got, as far as other names, frontal depressions, temperate cyclones, or extratropical, outside the tropical zone cyclones. They form between 40 and 60 degrees north and south latitude. They occur between 30 and 60 degrees north and south latitude. They can go out of that 40 range. That's why we're seeing the lower one there. Movement is west to east, driven or pushed by westerlies. They occur all year round in both hemispheres. The identifying feature is a warm front and a warm sector, and a cold front and a cold sector. Remember, we talked about how that cold front pushes faster than the warm front. It occludes, and you have that occlusion up here, and that warm front is then overtaken. So you've got basically it's overcome with cold air that's forcing the rapid rise of that warm air, and that warm air condenses and precipitates out. Weather associated with the cold front is overcast, low temperatures, strong winds, and heavy rain. With the warm front, it can be, again, kind of not heavy, but prolonged precipitation. Now, we're going to fill in cyclones here as we go. So the World Meteorological Organization, or the WMO, defines these four different aspects of tropical storms. We have a tropical disturbance. So this is a region of enhanced convection with light surface winds and a diameter of 200 to 600 kilometers, having a non-frontal migratory character. Tropical depressions, a weak tropical cyclone with a definite closed surface circulation and highest sustained wind speeds averaged over 1 minute or longer of less than 34 knots. Tropical storms, a tropical cyclone with closed isobars and highest sustained wind speeds between 34 and 63 knots, and a tropical cyclone, typhoon, hurricane, a tropical cyclone with highest sustained wind speeds of more than 64 knots. So we're getting into some pretty intense wind speeds at that point. Here we can see a infrared satellite image from 8 a.m. on July the 10th of 2012, showing 3 tropical systems over the eastern Pacific here. So we've got our Pacific Basin. So we're looking, the Baja Peninsula is right here. Mexico here. So we see a tropical disturbance, a tropical storm Daniel, and a hurricane. Now, just notice kind of the intensify. You go from 1 to 2 to 3. Disturbance, lots of cloud formation, things like that. Tropical storm, we see a little bit more contained, cyclonic, more circular pattern there with the most intense portion right there. And then Hurricane Amelia, you can see there is the eye right there in my circle. You can kind of see, remember these spin in a counterclockwise motion. You can see that really, really well there. So there are some conditions that are needed for hurricane development. Now, we're going to go over them. I've got the basic notes here, but I'm also going to be talking about them. So make sure to pause, rewind if you need to, try to get these down because there are a lot of really important factors for hurricane development. So the first we see one, ocean waters greater than 26 degrees Celsius. So the first condition is that ocean waters have to be more or have to be above 26 degrees Celsius, 79 degrees Fahrenheit. Below this threshold temperature, hurricanes will not form or will weaken rapidly once they move over water below this threshold. Ocean temperatures in the tropical East Pacific and the tropical Atlantic routinely surpass this threshold. Two, the second ingredient is distance from the equator. Without the spin of the Earth and the resulting Coriolis force, hurricanes would not form. Since the Coriolis force is at a maximum at the poles and minimum at the equator, hurricanes cannot form within 5 degrees latitude of the equator. So 5 degrees north, 5 degrees south, that whole 10-degree difference, you don't see hurricane formation. The Coriolis force generates a counterclockwise spin to low pressure in the northern hemisphere and a clockwise spin to low pressure in the southern hemisphere. Number three, the third ingredient is that of a saturated lapse rate gradient near the center of rotation of the storm. Saturated lapse rate ensures latent heat, so phase exchange or latent heat exchange during phase changes of water, will be released at a maximum rate. Hurricanes are warm core storms. So their core, the center, the core of the hurricane is warm. The heat hurricanes generate is from the condensation of water vapor as it convectively rises around the eye wall. The lapse rate must be unstable around the eye wall to ensure rising parcels of air will continue to rise and condense water vapor. Number four, the fourth and one of the most important ingredients is that of a low vertical wind shear, especially in the upper level of the atmosphere. Wind shear is a change in wind speed with height. Strong upper level winds destroy the storm's structure by displacing the warm temps above the eye and limiting the vertical ascent of air parcels. Hurricanes will not form with strong upper level winds. You need to have low upper level winds so that you can get that vertical motion to be sustained, basically. The fifth ingredient is high relative humidity values from the surface to the mid-levels of the atmosphere. Dry air in the mid-levels of the atmosphere impede hurricane development in two ways. First, the dry air causes evaporation of liquid water. Since evaporation is a cooling process, it reduces the warm core structure of the hurricane and limits vertical development of convection. Second, dry air in the mid-levels can create what is known as trade wind inversions. This inversion is similar to sinking air in a high pressure system. The trade wind inversion produces a layer of warm temperatures and dryness in the mid-levels of the atmosphere due to the sinking and adiabatic warming of that mid-level air. This inhibits deep convection and produces a stable lapse rate. We don't want stability if we want a hurricane. The sixth ingredient is that of a tropical wave. Often, hurricanes in the Atlantic begin as a thunderstorm complex that moves off the coast of Africa. It becomes what is known as a mid-tropospheric wave. If this wave encounters favorable conditions, such as stated in the first 5 ingredients, it will amplify into a tropical storm or hurricane. Hurricanes in the East Pacific can develop by a mid-tropospheric wave or by what is known as a monsoonal trough. There we go. Some additional facts. Hurricanes take energy from the warm ocean water to become stronger. While a hurricane is over warm water, it will continue to grow. Because of low pressure at its center, winds flow towards the center of the storm and air is forced upwards. High in the atmosphere, winds flow away from the storm, so convergence at the surface, divergence aloft, that divergence aloft is which allows more air from below to rise. So you kind of create this, basically not circulating pattern, but vacuous center. So air is rushing in, piling up, forcing itself upward, diverging aloft. That divergence is leading to it's like a suctioning of air up. The air that rises needs to be warm and moist so that it forms the clouds of the storm. Warm, moist air is found above warm tropical ocean waters. Makes sense. And a hurricane also needs the wind outside the storms to be light. These winds steer the storm, but are not strong enough to disrupt it. What is the energy source of hurricanes? Well, we kind of mentioned it already. Hurricanes get their energy from the warm waters off the tropics. Warmer bodies are more energetic than colder bodies. It requires that the water surface be at least 80, we talk 79 or so. It needs to be 26 degrees Celsius or greater. They also need that moist air through depth and weak wind shear. So you need a deep layer and low wind shear above. And they generally will develop as weak tropical disturbances moving over the ocean. So let's talk about the origin of hurricanes, not the concept of hurricanes, but the origin of hurricane development. So here we can see this is an easterly wave. This is a low pressure trough moving east to west. So a tropical wave moving off the coast of Africa over the Atlantic is shown here. The wave is shown by the bending of streamlines. And you see kind of these bumps here. Draw something that is a little bit better. These bumps here, right? So we've seen this symbol before. This green one here, that's a trough. If we recall, troughs are area of kind of defined low pressure, right? So we've got this kind of low pressure system here with winds kind of bending around that trough. The wave begins to move westwards slowly, bringing fair weather on its western side and rain showers on its eastern side. So that's kind of how we start. So here's another one. We've got our easterly wave here. It's still moving forward, but we start to get kind of more and more bending as we pass through these waves here, right? So if we look at that one above it, we see it pretty well. We've got our trough axes here. So here's a trough, here and here and here and here. So it's passing through those and gaining steam as it continues. So with that low pressure or these low pressure zones here, right, you've got convergence of air. And as it converges, you're kind of fueling this storm more and more and more. And it can begin to develop if it's defined enough. If we have, these thunderstorms moving off the coast of West Africa, moving into the Pacific or into the Atlantic, you've got the intertropical convergence zone. So you've got a ton of moisture in the area. You're moving over the ocean, so you've got a ton of moisture there too. You're in the equatorial region, so you've got a lot of heat. And that's kind of how we get this progression. So we go from an easterly wave or a tropical disturbance to a tropical depression. 10 to 25% of tropical depressions turn into tropical storms. 50 to 60% of tropical storms can turn into tropical hurricanes. So what do these look like? Well, they look like this. This is Hurricane Elena over the Gulf of Mexico, about 130 kilometers southwest of Apalachicola, Florida. This is in September of 1985. The central pressure of this storm in particular was about 955 millibars with sustained winds over 105 knots or 121 miles per hour near its eye. But you've got, recall, we're counterclockwise rotation here, so we're going this way. You've got a few things going on. You've got your eye here, your eye wall kind of on the outside here. So that eye sometimes can be, because it's the center of your system, sometimes things might not be going on necessarily in the eye, but that eye wall can be incredibly intense. That's your lowest pressure portion of the storm. Winds are going to be strongest. Meteorological phenomena are going to be densest. You might have a rain-free area kind of on that back edge of the storm. But as you kind of move in, you've got this kind of spiraling band of rain that we see here moving into the center of this system. So how do you rev up a hurricane, really? There are two positive feedbacks involving warm water. So convergence convection, so you have conditional instability of the second kind. So if we look at what's going on here, you've got at the surface, as that surface low is strengthening, you've got moist frictional convergence. Convection and the surface low have a positive feedback on one another. So at moist frictional convergence, convection, and the surface low all are feeding into one another. Winds strengthen as that low develops, feeding your frictional convergence. So converging winds, frictional forces, and then stronger convection of that air up. We see kind of circulating up here, gives more latent heat. So there's more heat exchange with that phase change of water. And then you've got that surface flux convection, or WISHY, you could say, wind-induced surface heat exchange. So these are the two things that are really working together in ways to feed and strengthen that hurricane system. So here we can see a cross-section of a hurricane. This is a model showing a vertical view of air motions and clouds in a typical northern hemisphere hurricane. Vertically exaggerated here, but we see kind of these, as we said, spiraling bands of rain. So we've got air. If we look from in to out, we'll use this left portion of the storm here. We've got air and condensation occurring, so rising air there, maybe descending air here, rising air here with rain, descending air here with not much going on, and it just alternates and intensifies as it does so. So the closer you get, the more intense that vertical motion is, and the more intense that storm becomes. And then you've got these rising conditions here. We see right in the center, and then outflow, so divergence aloft here. So major surface low, major altitudinal high, or aloft high. So here we're looking at this mass here. This is Hurricane Katrina's eye wall. This was photographed on the 28th of August from a NOAA reconnaissance plane. So kind of the eye would be then, here, and then we're looking at this big feature here. This is the eye wall, this whole space kind of cupping around here. So what are some characteristics of hurricanes? So this is typically what the path of a good number of a Cape Verde hurricane, those coming off the coast of Africa, Cape Verde, looks like. So 1 to 5 days, you've got your tropical disturbance here. You've got your northeast trade winds blowing down this way, kind of helping fuel that storm. 5 days, 5 to 6, you might have a tropical depression. We see here. Days 7 to 9, moving into the Caribbean, you might have a tropical storm. And then days 10 to 15, you could get a tropical cyclone or hurricane. And then maybe a subtropical high pressure system here. Prevailing westerlies, obviously, we're going on over here. Stationary front here. Moving into days 16 to 17 here. You've got extra tropical transition, so you've got kind of this cold air mass pushing down. You've got the warm front kind of moving from your storm here, so you start to see this storm starting to weaken. Here you've got that cold front again. Maybe it's still an extratropical cyclone. It can still produce a ton of rain. In fact, Hurricane Ida in 2018, after it struck Louisiana, moved all the way up and then slammed into New York before it finally started to peter out over as it continued off this way over into the Atlantic. So we're looking at late stage hurricane by the time we get here, where it's an extratropical cyclone. Here is the intensity and tracks of tropical cyclones globally since 1851. We can see some major hotspots, obviously, here going into Southeast Asia, here off the coast of Mexico, all throughout the Gulf and East Coast region of North and South America. So just to show on the bottom there, you can see the color is indicative of the strength. So the darkest orangish red is your Cat 5 or your Category 5 hurricanes. The lighter blues are your tropical depressions into tropical storms. So this is an idea of Hurricane Katrina. So this is rain rate estimates from Hurricane Katrina. So this is in millimeters per hour. We can see that spiraling band here, these rain bands, really, really well, going from left or from right to left there. So most intense in these spiral bands, least intense kind of in between them. We see here, here, and here. So this was satellite view that was passing over Hurricane Katrina on August of 28th. We're seeing those concentric bands, the red areas encircling the eye. So notice that the heaviest rain occurs within the eye wall, right here. The isolated tall cloud tower in the northern section of the eye wall here, here, indicates a cloud top of 16 kilometers. Such tall clouds in the eye wall often indicate that we're seeing an intensification of the storm. Here we're seeing Hurricane Dora, wind speed and direction. So these show that counterclockwise spinning around Hurricane Dora, situated over the eastern tropical Pacific in August of 1999. Colors indicate surface wind speeds. So in knots, so the zero meaning, or the purples, slow or non-existent. The reds and oranges, much, much more intense. And it makes sense what you see, right? So the arrows are vectors and directions. So longer means more intense winds, but also show directional vectors. But the color also shows that underneath as well. So most intense filling in here at the low pressure at the surface. So notice that wind speeds of 80 knots, 92 miles an hour or so, are encircling the eye. Wind speed and direction was obtained from NASA's QuickSat satellite, which gathered data from 1999 to 2009 and allowed us to see things like this. In much the same way as an ice skater spins more quickly as their arms are tucked, a hurricane also spins at a faster pace near the center than along the outer edges. So if we look here, this is a top diagram showing the intensification period of a tropical cyclone. So as latent heat is released inside the clouds, the warming of air aloft creates an area of high pressure. So here, which induces air to move outward away from the high. So that way, right? The warming of the air lowers the air density, which in turn lowers the surface air pressure. As surface winds rush in towards the surface low, they extract sensible heat, latent heat, and moisture from the from the warm ocean. As the warm, moist air flows into the center, it's swept up into the eye wall. As warming continues, surface pressures lower even more. So we see increasing vertically here, so we're seeing a dip near the center. And we're also seeing wind speeds peak up until the eye wall. So this situation increases the transfer of heat and moisture from the ocean surface. So that middle diagram illustrates how air pressure drops. The lower diagram shows how surface winds change. So as we mentioned, strongest in the eye wall, so this area here, on both sides. And we see kind of this void. So it's the lowest pressure zone in the eye, but we also see a major dip in winds as well. And that can actually be pretty deadly if people think that the storm is past when really they're just in the eye of the storm. So in our neck of the woods, the destruction is most intense on the right side of the cyclone, both in wind and storm speeds. So on the left hand, the hurricane is going to be, where net movement is this way. So as winds are kind of whipping around in that counterclockwise motion, they're going to be striking as they're coming into the coast directly onshore here. So that can be the reason for some of the most destructive aspects of the storm, is because not only do you have intense winds, you've got intense storm surge. So once it's come back around, it's blowing offshore. So net wind is offshore here, but it's been slowed down by things like the land. So you see our net vector here is substantially lower than our net wind here, which we call the fetch. The direction that the wind can flow over unimpeded is much longer on the right edge. So that can lead to some of the worst impacts of that storm coming into the coast. So we'll talk about storm surge here in just a little bit. So we're looking here at eye wall replacement. So a shrinking eye indicates storm intensification. Some intense hurricanes develop double eye walls as rain bands contract and intensify. Eye wall replacement leads to weakening of hurricane winds followed by renewed strength. So say, for example, you've got something starting to weaken, but then another section is picking up and intensifying even more. You can have that kind of eye wall replacement. So this is how hurricanes are more or less described by the Saffir-Simpson hurricane category scale. So category 1 through 5. So for 1, pressure, and we'll just use millibars, knots, and storm surge in meters, so we keep using metric. So central pressure is going to be greater or equal to 980 millibars. For a category 2, 965 to 979 millibars. 3, 945 to 964 millibars. 4, 920 to 944 millibars. And 5, less than 920 millibars of pressure. Winds for category 1, 64 to 82 knots. For 2, 83 to 95. For 3, 96 to 113. For a 4, 114 to 135. And for a 5, greater than 135 knots. Storm surges, which are some of the worst parts of a hurricane, meter and a half for a 1, 2 to 2.5 for a 2, 2.5 to 4 for a 3, 4.5 to 5.5 for a 4, and storm surges exceeding 5.5 meters for a category 5. Damage for a category 1, damage mainly to trees, shrubbery, and unanchored mobile homes. For a 2, some trees are blown down, major damage to exposed mobile homes, some damage to roofs of buildings. 3, foliage is stripped from trees, large trees can be blown down, mobile homes are destroyed, some structural damage to small buildings. For 4, all signs, like road signs and whatnot, are blown down, extensive damage to roofs, windows, and doors, complete destruction of mobile homes, flooding inland as far as 10 kilometers, major damage to lower levels of structures near the shore. And for a 5, severe damage to windows and doors, extensive damage to roofs of homes and industrial buildings, small buildings overturned and blown away, major damage to the lower floors of all structures less than 4.5 meters above sea level within 500 meters of the shore. So the hurricane category scale is perceived and expected damage as well as storm surge, wind speeds, and pressure. So it's kind of a mix of all these things. So let's look at what that looks like in video form here. So play our video. So this is intensifying as we get to a category 1. Notice, we're losing leaves and shingles on our buildings here. Category 2, we're losing a lot of shingles. Most of them are coming off. We're seeing debris flying. 3, we're starting to see the destruction of some of our trees that are starting to blow over, smaller ones, and our roofs are getting stripped. 4, our house is blowing away. Most trees are blowing down. And 5, nothing is left, basically. It can be pretty devastating to see something like a Category 5. To add some levity to the situation, oftentimes you see category abbreviated as CAT. So this is the hurricane wind scale in CAT form. Um, I'll let you pause on that and enjoy it for a second. I love cats, so this isn't me slamming cats, but I thought it was very funny given the more serious nature of what hurricanes are. So the greatest damage and loss of life, snapping back pretty hard, from hurricanes is near the coast associated with the storm surge. In the past, large death tolls have resulted from the rise of the ocean associated with many of the hurricanes that have made landfall. Hurricane Katrina, 2005, is a prime example of the damage and devastation that can be caused by a surge. At least 1,500 people lost their lives during Katrina, and many of those deaths occurred directly or indirectly because of the storm surge. Storm surges are an abnormal rise of water generated by the storm over and above predicted astronomical tides. Storm surge should not be confused with storm tide, which is defined as the water level rise due to the combination of storm surge and astronomical tides. This rise in water level can cause extreme flooding in coastal areas, particularly when that storm surge occurs with normal high tides, resulting in storm tides reaching up to 20 feet or more in some cases. Storm surges are produced by water being pushed towards the shore by the force of winds moving cyclonically around the storm. The impact on surge of the low pressure associated with intense storms is minimal in comparison to that of the water being forced by the wind. So it's not necessarily the pressure that's doing it, it's the wind that's doing it. So same thing we saw with the wind one. This is an example of storm surges. So as we're kind of increasing in intensity here, we can see it's just being exhibited by bigger and bigger surges. So you can see that profile view, we're breaching the wall or the flood walls or the levees there. So we can see in conjunction, maybe we're at category 3 now. So we're seeing major structural damage, trees being blown down. But that surge is the most devastating portion here we see. We're about 3/4 of the way through our video here, maybe getting into a category 4 at about this point. So not only are the winds incredibly sustained and high, the precipitation is incredibly high, but we're seeing intensification of the oncoming surge till our category 5, which we're kind of through now. So here we can see another view. So left normal high tide, category 1, a little over a meter, category 2, 3 to 4 meters, or sorry, category 3, 3 to 4 meters, category 5, 5 plus meters. So just again to show these kind of profiles here, um, with the storm is moving in this case left to right. So water on the ocean side flows away without rising sea level much, but on the landward side, you've got about pressure-driven surge of about 5% of the total surge, and then the 95% is driven by is your wind-driven surge. So causing wind or water to basically pile up as it's getting closer and closer to land. Here we can see beach homes before and after Hurricane Iva along the coast, Orange Beach, Alabama. So left before, right after Hurricane Ivan made landfall. So red arrows for reference, just to see some consistent buildings between both of them there. We can see before a hurricane, same thing after a hurricane. So we've learned how they form, but how do hurricanes peter out? How do they die? Well, they can weaken over land. So here we're looking at Harvey moving, making landfall and moving inland. It basically you're cutting off that moisture. So transforms into an extratropical cyclone, weakens over water due to hostile environmental conditions, so like strong wind shears or cool sea surface temperatures, leaving a remnant low pressure zone. It can be merged with or absorbed by a larger weather system or intersected by a frontal system or something along those lines. But basically, once you move over land, you can still have moisture coming into the storm, but you're cutting off that dominant source of moisture, which is moisture being convected off the surface from that converging air. So if we were to compare these here, tropical cyclones, other names, hurricanes, typhoons, or if you're in Australia, willy willies. Formation occurs around 5 degrees north and south latitude. They occur over tropical oceans, 5 to 30 degrees north and south latitude. They are east to west driven storms, driven and pushed by easterly winds. They occur mid to late summer and early autumn. Stormy weather in the vortex, the eye is calm, intense low pressure area, and then warm to hot, violent winds and intense thunderstorm activity. That's what we would expect to see as far as weather goes. So now just do a small little vignette on hurricanes in the United States. So this is a county-based map on the hurricane risk across the U.S. So we're not out of that risk. Well, we are here in Eau Claire for the most part, but these extratropical storms can still impact vast portions of the continental United States, not the coastal United States. But we can see areas like Texas, basically all along the Gulf Coast, Georgia, the Carolinas can be intense. They're pretty intensely impacted. If we were to look at North Atlantic tropical storms and hurricanes by year, this is through 2021, we can see an interesting trend here. So we see our tropical storms and depressions. Those are our yellows. Our oranges are category 1 to 3s, and our reds are category 4s to 5s. Now, there's been a lot of work done on this over the number of years, but what you're starting to see, more or less, and you can see it here, I'm going to draw on the top here, is if we were looking at a trend, that trend is doing something like this, isn't it? Let's draw it over here. Same kind of trend. Oh, ran out of mouse space. Here we go. We're seeing more storms and more intense storms. These are directly impacted by global climate change. Warmer systems, a warmer world means more evaporation. More evaporation means more energy being transferred into the atmosphere, more storms occurring. So we're seeing an intensification of hurricane patterns over the world right now. In the US, hurricanes making landfall in the United States occur mostly here, August, September, October. That's kind of the peak hurricane season here in the United States. 100 million Americans are at risk of for hurricanes. Almost 14 million live in an area where winds greater than 125 miles per hour have been recorded. This is the tip of Florida, North Carolina coast. More than 6 million live in storm surge areas. So areas that might not be directly impacted, but can be impacted just by the surge alone. We look at the deadliest hurricanes. Now, these don't always equate to the costliest hurricanes. The deadliest hurricanes from 1880 to 2010. We can see there was one in 1900 in Texas, in Galveston, before we really started to name storms. If we recall from a number of lectures back, this didn't start to really happen until the 1930s and 40s. That killed 8,000 people. It was a Category 4. In Florida, southeast Lake Okeechobee area, 2,500 people in 1928. Obviously, Hurricane Katrina in 2005. We see a few others as we go down, but some pretty incredible loss of life from these devastating storms. Now, if we look at costliest hurricanes, this is from Blake et al. 2011, updated and adjusted to dollars in 2017 when these figures were put out. Katrina, by and large, 160 billion USD. Harvey, shortly thereafter. This is right before Hurricane Ida came ripping through in 2018. Sandy, Irma, Andrew, Ike, Ivan, Wilma, and Rita. If you were to tally those up, that would be an incredible amount of money that we've had to spend on damages from these types of hurricanes. So if we were to look at billion-dollar events to affect the U.S. from 1980 to 2022, adjusted for inflation, 30 drought events, 37 flooding events, 9 freezing events, 162 severe storms, 59 tropical cyclones, 21 wildfires, 20 winter storms. Now, you might say, oh, well, there's more billion-dollar events from the severe storms, but if you look at the total cost of, say, severe storms, 374.1 billion versus extratropical cyclones, 1.2 trillion, kind of starts to put it in perspective. These are incredibly damaging storms. Highest loss of life potential compared to only to drought, and then severe storms after that, winter storms after that. Cost per year, 27.8 billion. Cost per event, 21 billion. This is from the NCEI or NOAA. It's one of the NOAA offices, and that says a lot, and it should say a lot. That's incredibly incredible numbers if you really look at it. Show just how damaging these tropical cyclones can be. Oh, sorry, I dropped something. So if we were to compare Hurricane Ian and Hurricane Katrina, so Hurricane Ian happened late last year, September 23rd to October 2nd. Hurricane Katrina, August 23rd to August 31st. Hurricane Katrina got to a Category 5. Ian got to a Category 4. Highest sustained 1-minute winds, 280 kilometers per hour for Katrina, 250 kilometers per hour for Ian. Lowest pressure, 902 millibars for Katrina, 936 for Ian. Fatalities, almost 2,000 fatalities for Katrina, over 150 for Ian. Damages or estimated damages, 189 billion for Katrina, 50 billion for Ian. Here you can see Hurricane Ian as it was moving through the 25th to 29th of September, 2022. There we go. You can kind of see it working its way up to going right over the panhandle, or sorry, not the panhandle, but right over central Florida. I'll play that one more time here. So here we see it getting up over 72, over into the hundreds of kilometers per hour, making landfall in Florida, kind of petering out as it goes over because that moisture is cut off. Winds are dying down a little bit. Here is Hurricane Katrina. This was a massive storm. Now, just let this play through a few times. It's pretty awe-inspiring. So this was a message. This is what went out. If you had been living in New Orleans or the area at the time, Hurricane Katrina, a most powerful hurricane with unprecedented strength, rivaling the intensity of Hurricane Camille of 1969. Most of the area will be uninhabitable for weeks, perhaps longer. At least one half of well-constructed homes will have roof and wall failure. The majority of industrial buildings will become non-functional. Partial to complete wall and roof failure is expected. All wood-framed, low-rising apartment buildings will be destroyed. Concrete block, low-rise apartments will sustain major damage, including some wall and roof failure. High-rise office and apartment buildings will sway dangerously, a few to the point of total collapse. All windows will blow out. Airborne debris will be widespread and may include heavy items such as household appliances and even light vehicles. Sport utility vehicles and light trucks will be moved. The blown debris will create additional destruction. Persons, pets, and livestock exposed to the winds will face certain death if struck. Power outages will last for weeks as most power poles will be down, transformers destroyed. Water shortages will make human suffering incredible by modern standards. The vast majority of native trees will be snapped or uprooted. Only the hardiest will remain standing, but be totally defoliated. Few crops will remain. Livestock left exposed to the winds will be killed. That's to be there in August 28th of 2005 and see that is unimaginable, I think, for us, and really, I think, puts into perspective just how much of an impact these storms can have in the regions that they do impact. So here we can see just another example. This is the 1900 Galveston, Texas hurricane. Greatest loss of life of any U.S. meteorological event. Over 8,000 died. This is the estimated track, moving over the Caribbean, intensifying over the Gulf, and then slamming into Galveston when it made landfall. And you can see there's basically nothing left of the area where it made landfall except piles of timber. And here we can see kind of another example. So from Galveston to Katrina, these are events that should be taken with seriously and with the utmost respect. But so those are types of tropical cyclones. That's what we talked about, our hurricane formation and characteristics, and U.S. hurricane facts. So next, the next group of videos, we're going to be moving into thunderstorms and tornadoes, moving into some, other aspects of meteorological phenomena. After that, we're going to move into some extreme weather phenomena, and then start talking about how we track and analyze and predict weather. So I hope you enjoyed that video, and we will see you in the next one. Thanks.